All right, welcome. This is Untitled Physics Live. This is GCSE Live on a Wednesday at 4:30. If you are not watching this live, then stick around. This is really good because this is going to be examiner feedback from the last year's exams, right? This is really, really important. I've got loads of stuff to go through, but it's such an important thing because actually, whether you like it or not, you are competing with the other people in the UK for those marks. You are competing for those grades. Okay, what we do is we take all the marks and we look at the averages and we work out what each grade is worth by doing that. So this is going to be a GCSE one. If you're an A-level student, then you're going to want to tune in tomorrow because I'm going to go through paper 3 feedback. That's all the practical stuff feedback, right? And the GCSE stuff might not be the most important for you. But okay, if you're GCSE, then definitely stick around for all of this video because there's going to be some such useful tips on what people weren't doing well last year, what people were, so you can make sure that you give yourself the best possible opportunity to get the best possible grade. Just going to say really quickly about my channel. I'm going to try my best to stick to a schedule for the next few weeks and see how that goes. I'm going to try and do like a motivation video on a Monday, a tutorial on a Tuesday, on Wednesday, this one, GCSE Live, on a Thursday, the A-level Live. So the lives are really good because you can ask questions, you can stop me, and I think people find that really, really useful, and we'll gear these up as we get towards the real thing. And on Friday, I'm just going to try and do something. I'm just going to do anything I fancy on a Friday, right? For 3 Fridays. I just did a thing on Monday, which was about homework, whether we should ban all homework or you can never have too much homework. Interestingly, the vote on my community tab, you can go and find it there. It's still going. Do vote what you think. And ban all homework is just a few percentage points ahead. Okay, it's pretty even Stevens, but ban all homework is coming out rather than you'd rather have more homework. And I don't know. Should that really surprise me? I don't know. But this is really important, especially if you've got your mocks coming up. Maybe you've got a triple physics mock tomorrow. Maybe this stuff might be really, really useful for you guys. Okay, so let's get into it. Okay, right. This is one of the main things is looking for the clues in the cues. That's what I'm going to say that quite a lot. Right, the clues that are in the questions to tell you what to actually answer. And all of this, remember, this comes from my experience as being an examiner, right? So I'm not really allowed to tell you which exam board I'm an examiner for, so I won't. But I am an examiner, and so I do see these things in, as I mark things, these common errors come up, and that's where most of this stuff is really from. Also bear this in mind. Add value to whatever it is that the question has said. There's so many people that are actually repeating what is in the question and expecting a mark from that. The clue is what's in the question, and whatever you could say above that, if you can use the data, manipulate it in some way, do a calculation to get an answer, that's adding value. Hi, Joel. I will stop periodically for any chat if you've got any questions, right? This is from a pretty large set of data, so although some of this comes from one exam board, it does really apply to all exam boards, okay? The standard was, we were all quite surprised at how high the standard was, especially in the triple science, right? We were really impressed with everyone last year, and so it's going to be another high standard this year. It's going to be even higher. And in fact, we weren't expecting this. The mean mark was higher this year than it was for the legacy specifications, and that's really, really impressive, right? Especially one thing was done really, really well. The calculations were done really quite well. So that's really, really good. So you need to make sure that you memorize your equations, and a quick plug for my book, Memorize Equations for GCSE Physics, which you can get on Amazon, is linked below. Loads of things are in here, and some of the things that people weren't doing well, they would have done well if they've taken this book and studied it properly last year. So that's just one way that you could learn some of those things. All right, here's some of the nitty-gritty stuff like rules for motion graphs wasn't done very well. So knowing exactly what's meant by a gradient or an area on a motion graph, a velocity time or distance time graph, right? And especially they asked one about a bouncing ball that was really tricky, and people struggled with the motion graph of the bouncing ball. So look at some really hard concepts and really hard to understand motion graphs would be really useful. The principle of moments wasn't done very, very well. So moments is this idea of seesaw, and normally it's going to be about an equilibrium, a balance between clockwise and anti-clockwise moments. Okay, so that should be a pretty simple one. Okay, really, because a moment is just a force times the distance, right? So you just need to look at the force times the distance on one side and make that equal to the force times the distance on the other side. So again, it's going to be one of these 4 things that you're not going to know, and the rest of them you are going to know. That's how you get at moments. It's just looking at an equilibrium situation. Yeah, questions where it just asks you to describe, right? Look out for these things. If it just says describe a graph, typically, people aren't getting easy marks there. They're not just saying, oh, it's a straight line. okay? It intercepts the y-axis at this. Or it's a curve with an increasing gradient or curve with a decreasing gradient. This section is a curve, this section is a straight line. Describe just says how it is. Don't have to explain why it is. And another describe one people aren't doing fantastic well is describing experiments, not just the core practicals. Yes, you need to be able to define all of the core practicals or PAGs or whatever your specification calls it really, really well. There will be 6 markers in there which should describe one of those core practicals. You can always bank on it. Somewhere in the GCSE there's going to be a describe a core practical 6 marks, right? But you need to also be able to describe other types of experiments and models that we do in science, that we do in physics to show things. So you need to have a really good, thorough understanding of experimentation and be able to come up even with your own experiments at times as really tricky questions. We need a bit more of a better understanding of electrostatics. On the face of it, electrostatics is just positives and negatives, attraction, repulsion, whatever, right? But when you get really deep into electrostatics, it explains why we have voltages and currents. And that's what people aren't getting, right? So you need to think about the idea of this field between point charges. Now that field could also be described as a potential difference. You've got a negative potential, positive potential. You've got a negative charge and a positive charge. But there's some energy involved in that because those charged particles don't all want to be there, right? And when we put some conductors or some charged particles in that field, they're going to start to move to either side. That's what potential difference is, and that movement of the charge, that's the current flow, right? So you need to have a really good idea of this idea of charge being the kind of fundamental property of electricity, and use that knowledge of statics to help you explain currents and things like that. Okay, and remember this, and I'll say this again because this comes up time and time again. Always add value, use the data, okay? Don't just re-quote it. So a lot of people are saying, look, this is this because that number's that and that number's that, rather than doing a calculation with them or even just comparing the numbers. This is this because that number is bigger than that, adds value to it, rather than this number is this and this number is that. Okay, so on 6 mark questions, this is the biggest tip that I always give. Spot the mini question. So a lot of people they're writing a good description of an experiment, but the mini question within that it says, make sure you mention how to be accurate. Make sure you mention how to actually get, how to do an accurate technique to get accurate measurements on this. Look for the cues. Look for the clues within the cues. Look for the clues in the questions, guys, that's going to tell you what is that. So 6 mark question is really 3 small 2 mark questions is the way I would think about it. You just need to identify those 3 questions. An easy one, like for, just a bit of knowledge that's basically new on the new specs. There's quite a few of these like bits that are new on the new specifications that maybe people's knowledge isn't good enough because they haven't had loads of past papers to practice. Okay, one bit of knowledge that's new on the new specifications is the idea of an elastic collision. So just a simple define what an elastic collision is. People weren't getting that. Elastic collisions conserve both kinetic energy and momentum. All collisions conserve momentum. Elastic collisions conserve both kinetic energy and momentum. So inelastic doesn't conserve kinetic energy. So there's a few bits like that. And here's another thing. A lot of people and a lot of teachers accept this, and they shouldn't, but we as examiners don't accept it. Gravity is not a force, okay? Gravity is a phenomenon. So if you're looking at a free body diagram, we're looking for the word weight, or just a big capital W to say it's a weight. mg would be acceptable, mass times gravitational field strength, but weight is the force, not gravity. We won't accept gravity. So remember, look for the clues in the cues. So here's the rest of it. Here's the second half. Hasn't been any chat yet, but if you do have any questions, that'd be really good. If you're new, if you've just joined, then you can go back at the end and watch the rest of it. This is the GCSE kind of feedback from last year's exams. People did really, really well. Here's how you can do better than the rest in this year's coming up. Don't forget to like it as well, this video, because that just tells YouTube that this video is worth watching. All right, so generally on the paper, people who did really, really well did this. Generally in the GCSEs, they managed to recall and to apply their equation. This is what this book is all about. It's not just memorizing, it's not just got flashcards, it's got some questions. So it's not just actually learn the equation, but actually practice using them. And in doing so, in practicing using them, you're going to make sure you can rearrange them, you're going to make sure you can put the numbers in the right place, and make sure you know the units and you can remember those. So don't forget to not just learn them, but practice using them, manipulating them, all of that. People who did well also were people who underlined the keywords, right? Now, teachers say this a lot, and I always say underline the command words. And the reason I say underline the command words is there is a command word for every single mark in a GCSE paper, right? Or, there might be one command word might be worth 2, like explain this, 2 marks. But everything is linked back to a command word. So the command word tells you what to do. And if you look and you underline the command words, you make sure you're answering the right type of answer for each one. Describe, explain, evaluate, that type of. Good students who did well, answered in depth, okay? So they could describe experiments in depth, not just measure this, measure that, calculate that. They said what to use. They said what apparatus to use. They said exactly the methodology to use it and how to be accurate. The techniques like measuring 10 full swings and dividing by 10 to get a time period, that type of thing. They work methodically, okay? They get rid of the distractors. You can see them crossing out the ones that don't make any sense in the multiple choice questions, that type of thing. They describe methodically, so they pause and they think about their descriptions before they answer, especially 6 markers. They have a little plan in their head at least, maybe a little scribble down point 1, point 2, point 3 before they put pen to paper. The students who don't do well, I always find they're already halfway down the answer box before they've said anything useful because they've just started, well, you go ahead and you do this, and it's just like, you can tell they're thinking as they're writing, and that's probably not the best idea. And here's one, people who didn't do well, they didn't know their unit prefixes. For example, this one, okay, do you recognize that? That's a micro symbol. It means times 10 to the minus 6, right? That's a micro. So you might be familiar with milli and kilo and things like that, but you might not be familiar with micro, and you need to know all the way up to tera, which is times 10 to the 12. Again, they're all in this book, Memorise Equations for GCSE Physics, which you can buy on Amazon or you can download on your Kindle as well. And what people are doing when they do it well, hi Ultra Game, what people are doing when they do it well is they're seeing that prefix and they're just banging into their calculator. Rather than doing any thinking about it, they're just putting on times 10 to the minus 6 instead of the mu, instead of the micro. Right? If they're seeing a milli, they just think, okay, just type in times 10 to the minus 3. That's a really, really useful thing. And they're all in that book. So students who didn't do very well, they couldn't do the manipulation of equations. They didn't have the kind of knowledge necessary. Now there's this huge amount of knowledge necessary to do well in 9 to 1 GCSEs. The focus on remembering stuff is really, whether you like the merits of that or not, is, we can talk about that for a long, long time. Whether that motivates you or not, we'll talk about that for a long, long time. But if you want to get the best grades, you're going to have to go a lot of memorization, a lot of just remembering your equations, remembering how to use them, remembering key kind of facts that will help you get those marks on the paper. So if you want the highest grades, you've got to do the memory work. What else? Specifically, didn't remember equations for power output and power loss. That's P equals I squared R. Okay, that's power loss in power lines. Specifically, didn't remember the equation for like calculating reaction time. And reaction time, well, that's going to be a distance over a speed, but it's specifically the thinking distance over a speed that gives you the reaction time. So that would be a useful one to just memorize, really. People who didn't do very well, they didn't show calculations. They just wrote down a bold answer without any calculation. And if that's wrong, if there's just, you haven't rounded it correctly, anything like that, then you're going to not get any marks. Whereas the way we mark the calculations now is actually more generous than it used to be. We actually give more marks for step-by-step calculations, and seeing those is really, really useful. And they don't have responses that lack depth, probably because of their lack of deep knowledge. Okay, and that's what I'm talking about, the memory stuff. I'll pause for that question. I do actually have a video saying why is A-level so much harder than GCSE. It's basically because it all starts, the main thing about A-level is it starts higher up. So you don't get many just remember questions in A-level. That's the main thing. You start from this kind of explain, apply, that type of thing. What was that? That looked like a decent question, and I'll get back on with this thing. About to revise A-level Chem. I also do Physics, which I got an A-star in previous exam. Good luck, everyone. All right, thank you very much, Yo Gamer. Hope you're doing well in your A-level Chem. All right, enjoy it. Mock exam, I take it you're all in the middle of mock exams at the minute. Hope this is useful. I know some people have a mock physics tomorrow, so this hopefully will be useful for them. Shout out if you've got a mock physics tomorrow. Hit a like button if you're here, because it just sends to YouTube this video was worth watching, and it puts it in front of more people. So to do that for me, please. Okay, so let's carry on then. So the least successful kind of things in this paper were things about beta radiation and penetration, right? We learn about what can these 3 types of radiation penetrate. We learn they can, alpha can only penetrate a few centimeters of air and very, very thin paper. We learn that beta can penetrate 2 millimeters of aluminium. We learned that gamma can penetrate up to like 10 meters of lead. Okay, now that means that it's stopped by lead, but it means it can penetrate some lead. And here's where people are getting things wrong, because they're thinking, no, they're thinking all a type of radiation will be stopped by just very, very thin lead. And specifically, the question was about beta, and they were talking about aluminium foil. Now, beta will go through very, very thin aluminium. It'll be stopped by 2 millimeters of aluminium. So beta was useful for measuring the thickness of a sheet of aluminium foil. Remembering your satellite orbits was difficult, okay? Understanding this idea, the further they are, lower force, lower speed as well, the further away they are from Earth. So if you're closer to the center of gravity of an orbit, then you're orbiting faster. Higher force as well, orbiting faster. Estimating forces, again, it's a new bit in their new specification. So coming up with some typical forces for like riding your bike, or typical forces, orders of magnitude type thing for driving a car. So driving a car, we're into the thousands of newtons. Riding a bike, we're in the hundreds of newtons. That type of thing. Okay, you're estimating things like typical speeds when you're riding a bike or walking or driving a car in meters per second, and converting between miles per hour and meters per second, something that people aren't doing all that well. Refraction, and understanding and explaining that as a consequence of change in speed. Right, so in refraction, the fixed thing is frequency. Wavelength changes, speed changes. I'm going to come back to this in a minute. In refraction, frequency is fixed. The other two things change, right? And it's because of a change in speed that it changes direction. So bigger change in speed, bigger change in direction, more refraction. People aren't being specific enough on pollutants. They're saying that's bad because it causes pollution, but they're not saying what type of pollution. They're not saying causes CO2 to be released, which it causes the greenhouse effect, which leads to global warming. They're not being they're not being specific enough, or they're naively thinking that actually nuclear is renewable because nuclear isn't about CO2, and that's not the definition of renewable at all, is it? So not all renewables are 100% positive. There are negatives, there are downsides to all types. And this is why we talk about that topic as being evaluating energy resources. So you need to have a really detailed understanding of energy resources and power stations and things like that, all their advantages and disadvantages, and be able to apply them to a context. I've got a good video about geothermal that I did when I was out in Iceland that you should probably check out if you want to understand some really tricky questions they're going to ask us about evaluating energy resources. Right, there's this misconception though about power lines and why we have higher voltages. People are talking things like energy moves faster. That's not the case, right? It's not about energy particularly, right? Higher voltages in power lines reduce currents. So here's what I want you to remember about power lines. I want you to remember P is I squared R. And I want you to remember this as power loss equals current squared times resistance. The resistance of the power lines is fixed. The current, if we increase the current, then we get a lot more power loss. And it's not proportional to current. If we double the current, we get 4 times the power loss. So I want you to remember this equation, not as power is I squared R, but as power loss is I squared R. And if you do that, then hopefully you're going to be able to use that. And apply that to the questions when it's asking you about why do we step up the voltages in a power line? Well, to reduce the current, to reduce the power loss. And it's because of the heating effect of current. I've got a great video which I really enjoyed doing about the heating effect of current, where I heat up some graphite. So search that. Heating effect of current is a useful thing to do that. Dan, I will answer your question about interested physics just almost at the end of these tips, and I want to hit them because I know that not everyone particularly wants to stay to that, but these are important points. If you missed the start, go back to the start. These are important points that people didn't do well last year or did do well last year, and you need to be better than everyone else if you want the top grades in these GCSEs or the A-levels. And tomorrow I'll do A-level paper-free practical physics, the feedback from last year's ones of those. Yeah, this equation here, right, V is F lambda, means wave speed is frequency times wavelength. And people, I think, aren't the lights are gone. Yeah, a bit spooky, but anyway, we'll crack on. I think we're okay. Wave speed is frequency times wavelength. Now, wave speed is fixed in a given medium. It's fixed if we're talking about in water, we're talking about a specific depth of water. That's fixed wave speed. If we're talking about a string, specific thickness of string, specific tension in this string. That wave speed is fixed. So if the wave speed is fixed, then frequency and wavelength are inversely proportional to one another. If you double the frequency, you have to halve the wavelength for the wave speed to be fixed. I think people are misunderstanding that because they're thinking, oh yeah, if I increase the frequency, well, I must increase the wave speed. We're talking about these two changing and this one being fixed with that equation. Also, people versed in like the experiments or the demos or the models that we use to explain things. So for example, waves, one of the definitions of waves is that it transfers energy, not material. So how do you do an experiment to show in water waves that it's not actually the water that's moving along, it's actually the water's moving up and down. It's energy that's moving along. They're transverse waves. So the oscillation is up and down, and the water particles are just going up and down, the energy is moving along. So what if you put like a cork in that, what if you put a cork in the water there? It would float, it would bob up and down rather than be pushed along. So that's a demo that we can do to explain that key idea, that you need to be well versed. It's not a core practical, you need to be well versed in explaining that, right? That's what science is. It's experiments, it's demonstrations, it's models, okay? It's not just knowledge and knowledge and knowledge, but you need to be well versed and have that knowledge to actually get that experiment down on the page there. Again, there's another 6-mark question where they ask for accurate techniques, right? And there's another little part in the question that's giving you a clue in the cue to get all of the marks, to pick up as many marks as possible. Look for the clues in the cues. Right, here's the bit we're just going to go through the prefixes, because people were asked about EM radiation, and that's typically where you're going to find these prefixes. Okay, so here they all are. Okay, they're all in this book as well. There's a nice little page, nicely set out. You could screenshot this if you can't be paying for it or you can't find it where it is for free. But this is basically the ones you need to know. So tera is times 10 to the 12, giga is times 10 to the 9, mega is times 10 to the 6, kilo times 10 to the 3, deci, but you're probably not going to use it in physics, times 10 to the minus 1, sorry, deci. Centi is times 10 to the minus 2, you know that's centimeters. Milli is times 10 to the minus 3. Micro times 10 to the minus 6. Nano times 10 to the minus 9. You might, and I don't think they would ask you this, but pico is times 10 to the minus 12. You would be in A level. But so you've got to know those ones, okay? And the simple idea is basically you see the letter for the prefix. Instead of actually writing that down, that letter, just write down the multiplier, write down the times 10 to the. So if you see the micro, you write times 10 to the minus 6. And then that's what you can type into the calculator. Okay, next thing, so ultrasound benefits of that. People thinking ultrasounds actually cause mutations. That was a little bit of a surprise. Defining contamination and irradiation. Again, this is a new part in the spec. They want you to know the difference between contamination and irradiation of radioactive materials, right? So contamination means the actual radioactive source has leaked. The actual radioactive source has got on something that's staying there, so it's continuously giving out radiation. And that, therefore, is a longer term issue than irradiation. Irradiation means you've been hit by, something's been irradiated, it's been hit by some radioactive particles. That's not as bad necessarily because that's shorter lived. There's no radioactive source being there. So think about radiation is different from a radioactive source. Right, a source of radiation is different from the actual radioactive particles themselves. So the radiation can be alpha, beta, or gamma, and the radioactive sources is like the uranium or the carbon-14 or whatever, right? If you're here at the minute, hit some like buttons to let YouTube know that this is good and this is worth watching, please. So reaction time, what does Pewd say? Pewd says smash like, everyone, let's do that, please. Reaction time, remember the equation for that is thinking distance over speed. That's a really easy one if you think about it, because that's just good old speed, distance and time. But people are getting confused with which distance to use to calculate the reaction time. So that's thinking distance over speed. And lastly, energy stores and transfers, a new bit in the specification. They'll be testing it hard. They did last year. They'll be testing it again. Think about which store you start with. Think about what it is stored in, right? So it's the thermal store of something. Think about which store, think about which transfer, and which store it ends with. So here's my for example, right? We've got the kinetic store of a car, and that's transferring by mechanical work to the thermal store of the brakes or the surroundings. So let's get all that right, okay? Kinetic store of the car. It needs to say which kinetic store it is. Mechanical work is the transfer. It's transferred by forces. Frictional forces, you could say friction between the brake pads would be good enough. And that increases the thermal store of the brakes or the surroundings. So one store decreases, the other increases. If you think about that, 8 stores, 4 transfers, and you identify which store of what, and you think about the transfer, you're going to get those energy stores and transfers questions. Right. Look for the clues in the cues. That's the tip from the examiners, really. We write questions in such a way that you can get it, you can understand what we're after from the way in which the things we've included and the things that we've left out, basically. Okay, guys, let's have a little look through the chat and then I will go for my dinner. Be nice. When did I have an interest in physics? A level, basically. I just needed to do something at A level. I don't have a physics degree. Probably you're all going to leave now. I have an architecture degree, actually, because my main passion would be art, actually, interesting enough. But the architecture degree has enabled me, I think, to do this type of thing, to have the skills to do good videos and stuff like that, right? When did you, I said that, when do you have an interest in physics? For me, physics is about this tiny little particles and the massive universe and the kind of parallels between studying the particles and the universe. That's what I really, really love about physics is the tiny, tiny, tiny things, times 10 to the minus 20 scale, and the kind of, well, I don't know, infinite scale, you could say. We don't know, do we? It's fascinating, right? Chat. Well, why can't I see that? There it is. Okay. Do you need to be unusually weird to do physics at a higher level? Okay, that's interesting, right? I don't know. I say I don't have a degree, so maybe not. I don't think so. I think you need to be interested. I think you probably need to have a really confidence with maths. You don't necessarily need to be massively amazing at maths. You need to have a confidence with it, not to be put off by that. I think you just need to be interested, really. And sometimes I think to myself, well, the stuff in physics is the most interesting stuff at school. That's why I'm a physics teacher. I think actually it is the most interesting subject, certainly at secondary school. What else we got? Any advice on density? I struggle with density, nuclear fission, and nuclear fusion. Density. Well, density is like, it's often called heaviness for size, but it's a time when you need to just make sure that you go to equations, right? So density is mass over volume. This is your key kind of understanding for density, mass over volume. That's a rho, little m, and big V for volume. And really that's it. It's how many kilograms per meter cubed. I think probably where people struggle with that is the prefixes things, because you can do centimeters times centimeters times centimeters, and you get centimeters cubed, right? Now that looks on the face of it like that prefix should be times 10 to the minus 2, centi. But actually, if you're trying to convert that into meters cubed, well, there are 1 million centimeters cubed in a meter cubed, and that's because you've had to do 100 centimeters times 100 centimeters times 100 centimeters to get 1 meter cubed. So I think that's probably it. Does that answer your question? I mean, does that get you some way? If you're struggling with any type of physics, then look at the equations, really focus on the equations. Fission and fusion, get your head around the idea. Fission is because it's a very unstable nucleus, and it's splitting to become 2 more stable nuclei, and that gives out energy in the process. Fusion is tricky because what we're doing is essentially we're bringing protons together, we're bringing hydrogen together, hydrogen nuclei, and we need to have very high force to force them together. But when they do, they fuse into something, again, more stable. They fuse into a helium nucleus. Helium nuclei happen to be the most stable thing. So with all nuclear stuff, it's about becoming more stable. They ask you questions that actually, on the face of it, they're just to tease out the spelling difference between fission and fusion. So some questions can be really easy for that, some questions quite hard. I hope that helps you with that. I'll have a little think because I need to update my fission and fusion video because it's one of the first videos I actually did was fission and fusion. You can go back and find it. I think it's okay as a video, but there's loads more. All right, what else? I've got a month to my marks. I've memorized the equations in the first half of your book. Do I memorize the second half in the time I have left, or do I do past papers and questions? I would get them all memorized, but also like past papers and questions, you'll be practicing it anyway. I don't know what's coming up in your mocks. My kids are going to do a full thing, so I would encourage them to have done everything. I would certainly say by Christmas time, you want to have studied everything, even if your school hasn't covered everything, because you don't want to be there thinking, oh, there's a brand new bit right at the end of the course that I struggle with. And I would probably even focus on at the end of my book, and I think I'm going to write some more of these. There are these kind of 2-step calculations that are quite tricky. That's worth going to and having a go at those really quite tricky questions. I hope that helps, Andy. Was that Andrew? Yeah, nice one. Very well explained. Unusual to see someone go over so many different things well in such a short amount of time. Yeah, I felt like I was just blitzing through it all, Jack. I don't know, I hope it was well explained. Yeah, I don't know. I hope that was really useful to you. Those are some of the things that loads of kids got wrong. And if you do things better than people did last year, you can probably presume you're going to come out with one of the better grades. Okay, can you do well in physics without revising? Any advice on that? And I'll turn that one. Really weird. Planck's constant. Yeah, that's correct. Well done, YOLO gamer. Yeah, that's another one. All right, dudes. Motivation to study now because you want it, Joel. Okay, right? Because you actually want to do well in these. You want to know. You want to do well in this, so you can get onto the next step, so you can find out more, so you can be involved in things like, well, they've just landed on Mars again, so you can do, you know, excellent things in your life, but also just because you just want to know, right? Motivation to study. If you're not actually enjoying study, then change it up, right? I know that sounds silly, because who likes just to sit and kind of get the grips with some books? Change it up, do something different, try what I do, try explaining it out loud. Actually, this is testing, yeah. So somebody Jack just said, oh, this is a lot of information very, very quickly. This tests me out. It makes me better in the classroom because I'm like, oh yeah, I had to explain that on the video under pressure the other day, live in front of people, and you know, that makes you understand things better. So that's a really good tip probably for revision. You know, like make something. Make a little video. Now you don't have to share it with everyone, but if you make a little video on your phone, well, you can watch that on the bus with your headphones in. Okay, and you think, no, I didn't explain that very well. I must not understand that bit. I'll read up on that again, and I'll make a better explanation. You know, make yourself a set of flashcards as well. Do things that you actually kind of enjoy. Find out about stars and about everything like that, and how all these little things they actually, you know, all the basics of physics that they apply to stars and they apply to all the fascinating stuff, maglev trains and everything like that. That's really, really fascinating. This Falcon Heavy's going off again, you know, like he's on his way to Mars. You know, like he'll be doing what he's doing on Mars. So I don't want to lower the tone a little bit. How can you explain motion? Because I struggle with this. And how do you remember the right equations for the right question? Yeah, Candy, like loads of people struggle with motion initially. Have a good motion play. I think really it's kind of going through. There are motion topics tricky for people because there are so many equations to learn straight off the bat. I think hopefully you've done motion quite early in your GCSE, and by the time that you go back over motion, you should be a bit more confident with using equations and manipulating them, stuff like that. And hopefully the second time you look at it, it will start to make sense. Most people find motion really difficult first, and then the second and third time they go through it, it starts to click into place. Things like units, focus on units, you know, speed is distance over time, that's meters per second, distance over time, meters and seconds. Acceleration is meters per second or meters per second squared, because it's speed divided by time, changing speed divided by time, so it's meters per second, right? Yeah, I'm an examiner, dude. I'm going to go now. All right, thank you very, very much for watching. Not all teachers are examiners. No, there's no kind of, you know, I think a lot of us do it. It does pay, but also I do it mainly because I think it improves me in the classroom, and it says that I can say with confidence that is worth a mark or that isn't worth a mark. You need to just change this little bit of your answer to get this right. All right, dudes. See you soon.